Okay, here we are on page 4 of the HL addendum for probability. Last 3 problems. Number 7. Probabilities that Hiran's mother and father will be alive after 10 years are 0.99 and 0.98 respectively. What is the probability that if only one of them is alive after 10 years, it is his mother? Okay, so let's take a look at, let's see, the probability that the mother will be alive is 0.99. Probability that the father will be alive after 10 years is 0.98. Oops. What is the probability that if only one is alive after 10 years, it is his mother? So, probability that the mother is alive, given that either the father is alive and the mother is not, or the father is not and the mother is. Okay, so let's draw a probability tree for this. So first, mother alive, mother not alive, father alive, father not alive. Probability of the mother alive is 0.99. Probability of the father is alive is 0.98. 0.02, 0.98, 0.02, 0.01. Probability that both the mother and the father are alive are 0.99 times 0.98, which is 0.9702. The probability that the mother is alive and the father is not .0198. The probability that the mother is not alive and the father is 0.01 times 0.98. 0.0098. And the probability that both passed away, very small, 0.0002. Okay, now they say, what is the probability that the mother is alive, given that one of them is alive? So one of them is alive, that would be this case, and it would be this case. So basically we would have the case that the mother is alive, which is 0.0198, divided by both added together, which would be 0.0198 plus 0.0098, which is the two added together. That would be the denominator. And the numerator would be 0.0198 divided by that denominator. And that gives me 0.669. So the probability that it would be the mother that would be alive would be 0.669. Okay, number 9 is a proof or a demonstration. So this is kind of a weird Venn diagram here. It's got the universe divided up into 3 sections, which all include the event A. So basically event A fills the universe. Okay, so basically every single possible thing that can happen, A does happen. And then B is a subset of the universe and also a subset of the event A. So normally what we see is A like that and B like that, but in this case what they're saying is A happens all the time. So that's why we get this weird one. Okay? So first they say, okay, show that probability of B happening is equal to this. So basically, to do that, what we need to do is say, okay, the probability of B happening is this part of B plus this part of B plus this part of B, which is pretty obvious, right? So we'll call this part of B, B intersect A3. We'll call this part of B, B intersect A2. And we'll call this part of B here, B intersect A1. So actually the probability of B happening is equal to the probability of B intersect A1 happening plus the probability of B intersect A2 happening plus the probability of B intersect A3 happening, right? And we could also rewrite each one of these intersections using conditional probability. We could say the probability of B intersect A1 is actually the probability of B given A1 happening times probability of A1 happening, right? And then this one is equal to the probability of B given A2 happening times the probability of A2 happening. And this one is the probability of B probability of B given A3 happening times the probability of A3 happening. And that's exactly what we were supposed to demonstrate. Okay, so that was A. B, hence show that Bayes' theorem for the case of 3 partitions is equal to this. Okay, so let's see. If we have the probability of A1 given that that B happened, isn't that equal to the probability of A1 intersect B divided by the probability of B happening? So wouldn't that also be equal to, if we just take the top part and we say A1 intersect B, isn't that the same thing as the probability of, now I'm going to rewrite something down here. Probability of B given A1 happening is equal to the probability of B intersect A1 happening divided by the probability of A1 happening, right? So I could rewrite this as the probability of B intersect A1 happening is equal to the probability of B given A1 happens times the probability that A1 happens. Okay? And probability of B intersect A1 is the same thing as probability of A1 intersect B, right? So now what I'm going to do is I'm going to rewrite the green part as probability of B intersect A1 happening times the probability of A1 happening. Now I keep the denominator, which is probability of B happening. And I could rewrite this for A1, A2, and for A3. So that's basically what they wanted us to show here, okay? That it's true for 1, 2, and 3. Number 11. 12% of the over 60 population of Argento have lung cancer. Of these with lung cancer, 50% were heavy smokers, 40% were moderate smokers, and 10% were non-smokers. Of these without lung cancer, 5% were heavy smokers, 15% were moderate smokers, and 80% were non-smokers. A member of the over 60 population of Argento is chosen at random. Find the probability that the person was a heavy smoker, has lung cancer, blah, blah, blah. Okay, so basically we need to make a tree and of the over 60 population. And let's see, 12% have lung cancer and the rest don't. So let's have lung cancer and the rest don't. So lung cancer would be 12% and the rest is 0.88. And of the 12% that have lung cancer, 50% were heavy smokers. 40% were moderate smokers, and 10% were non-smokers. And of those without lung cancer, 5% were heavy smokers, and 15% were moderate, and 80% were non. Okay. And let's multiply these out. So, for example, cancer intersect with heavy smoker is going to be 0.06. Cancer intersect with moderate smoker is going to be 0.048. And then cancer intersect with non-smoker is going to be 0.012. Non-cancer intersect with heavy smoker is going to be 0.88 times 0.05. 0.88 times 0.05 is 0.044. 0.88 times 0.15 is moderate smoker with not cancer, 0.132. And non-smoker and non-cancer is 0.704. Okay. And let's see, what was the probability given that chosen at random? Find the probability that the person was a heavy smoker. So a heavy smoker is going to be just the probability. Let's see. Heavy smoker would be this one, and it would be this one. So it would be 0.06 plus 0.044. So 0.06 plus 0.044. So that would be 0.104. So 10.4% basically. Has lung cancer given that the person was a moderate smoker. So given that the person was a moderate smoker means here and here, that would be the denominator. And the numerator would be lung cancer intersected with moderate smoker, which would be this. So in the numerator, I would have 0.048. In the denominator, I would have 0.048 plus 0.132. So let's see what that is. So 0.048 plus 0.132 is the denominator, and the numerator is 0.048. Oops, divided by that. So it's 0.267. Let's check that. Yes, okay. And then finally, last one, has lung cancer given that the person was a non-smoker. Okay, so that would be non-smoker, oops, let's choose a different color. Non-smoker and non-smoker, what's the probability that they have cancer? That would be this, oh, why do I always choose green? Okay, so for the last one, it would be 0.012 in the numerator, and in the denominator, I would have 0.012 plus 0.704. So that would be 0.012 plus 0.704. That would be the denominator. And the numerator would be 0.012. Oops, divided by the denominator, 0.0168. Okay, and yes, that's correct. That's it.